So let me start the second lecture by giving a little recap of the first one. So what was the idea? The idea was to define an ensemble of the microdata of some quantum system, which is consistent with the thermal correlation functions. And the idea is that that defines a multi-matrix model, because we can think of the microdata means the Hamiltonian and other operators that we're interested in observing about this system or calculating. So I might have, this is not a good pen. So we have the Hamiltonian, we have some operator O and maybe other operators, and knowing the microdata means knowing these matrices. And so if we, instead, we usually know about a system as the thermal correlators, some low point thermal correlators, and then we can ask what is the possible microdata consistent with those correlators, and that will define some kind of ensemble of these matrices, which we can think of as a matrix integral over H and O, and it may have a piece which looks single trace, and then there could be multi-trace pieces, but the multi-trace pieces will also be suppressed by powers of e to the minus s, so the whole model has a consistent 1 over e to the s expansion, where s is the entropy.
So Daniel?
Yep.
You're trying to extract H from low point thermal correlators? This is the effort? No.
Not only H, but also the other operators. Yeah. So if we only measured the thermal partition function, then we will only be discussing H, and then we'll have an ensemble of a random matrix, and this will be random matrix theory for chaotic systems. But if we also have other kinds of correlators, then we get other operators, so now we have a multi-matrix model. Okay, so that's kind of the generalization. And this thing also incorporates what people call the eigenstate thermalization hypothesis, which is what you get by, imagine that somebody already determined H, then we write the model in the eigenbasis of H, and it looks like an ansatz for a random operator O, and if this potential was Gaussian in O, that would be the conventional ETH, the eigenstate thermalization hypothesis ansatz. But this kind of generalizes that to, nobody tells you that this potential has to be quadratic in O, it can be anything. And one tries to determine this potential so that it is compatible with the thermal correlators of whatever the system is that one has in mind. Okay? So that was kind of the framework. And maybe just to say a word about the timescales, which some people ask me about. If we have a quantum mechanical example or a lattice system, then we may imagine that in the UV, the theory looks free. So, something like the SYK model at fixed couplings at very short times, one sees that it looks like a bunch of free Majorana's at very short times. Maybe we have a lattice at very short times, you kind of see the underlying degrees of freedom. So maybe this toward the extreme UV, we might have some UV free at very short times. This is short time. And then at some point, the theory becomes effectively strongly coupled. And that's the time when we might discuss this kind of matrix ensemble. This is not very meaningful in the regime where you see the underlying free UV degrees of freedom, because then you won't think that, say, the fermion operator is a random operator in the regime where you can describe it by the Dirac algebra. Okay? So this is sort of the matrix time. Starts here, once the theory is strongly coupled. In terms of whatever are the original UV-free variables, if there is such. If we have a theory which is like a strongly coupled conformal field theory, this time scale goes all the way, right? There's no UV-free region. But in something like the SYK model, then we have to come up to there. And then, as we go to longer times, so in this initial region, they're out-of-time ordered correlators, which are not zero. It hasn't yet fully scrambled. And then we need a matrix model of this general type. But once we reach the point where the out-of-time ordered correlators are zero, that's when the Gaussian in O approximation is good. That was because of this reason that if we look at a 4-point function of 4 O's, the out-of-time ordered correlator is this sort of crossed contraction. And if we compute this in this matrix model, this becomes a 't Hooft diagram. And if it's Gaussian in O, there's no way to cross the lines at the planar level. And the non-planar thing is suppressed by e to the minus s. So that's fully scrambled. Okay? So, but as we go up in time, then the out-of-time order correlators may decay to 0, at least if we don't have any conserved currents. They will decay for all operators to 0, and then the Gaussian approximation to this matrix model is good. Gaussian for all. Then we have.
Daniel, but maybe put some. What is it? What are those times in terms of the entropy? I guess.
Well, this depends really on the system. So if we have a large M system, then this is the scrambling time, which would go like, beta log n, where n is the number of degrees of freedom. That would be a typical scrambling time. This is kind of very system dependent. So it's just not universal. It's a time when the theory looks not UV free anymore. So that's very non-universal. Yeah, this is all kind of very non-universal. But it's still possible to capture it in these matrix models. That's kind of the point. And then, so then there's this region where this time scales where for most of the operators we can treat the model as Gaussian. The non-Gaussians don't matter anymore. But if we have operators that are like conserved quantities, then their non-Gaussianity doesn't yet go away. Like for the Hamiltonian itself, for example, or if there were other conserved quantities. That's because the out-of-time order correlators of conserved currents do not scramble. Okay, and then at some much later time scale, which we might call the Fowler's time, although different people mean different things by the Fowler's time, so this is just kind of one definition of it, which is when, if one computed something like the spectral form factor, you're in the ramp region. So this is the time scale where, so here the matrix model looks Gaussian in O, but still you can't forget about O. So if we integrate out O, we get a contribution to the effective eigenvalue repulsion for H. Again, suppose we wrote the thing in energy eigenbasis, and this was quadratic in O, then in this region we would have something that looks like e to the minus sum over the energy eigenvalues, Oj squared, some function of the energies. And then when we integrate out O, we get log of this thing, which is a correction to the eigenvalue interaction. That will change the shape of the ramp. Okay? But once we go to longer time scales, it becomes universal. The reason why it becomes universal is because as we go to longer time scales, we're probing smaller energy differences. And the functions that appear here don't have any singularity as the energies get close. So eventually the Vandermonde, which just comes from diagonalizing the matrix, which which looks like EI minus EJ squared. This thing, well, if we take its log to write it as an effective action, sorry, it keeps making that sound. Maybe if I remove this, I don't know if that's what it's doing. Okay, yeah, maybe I think that was what was doing it. So if I write, oh, I guess not. Huh. Very weird. Maybe it's just interference, I don't know.
Maybe it's just too close.
Oh, okay. Okay, let's see. Is it still audible? Yeah. Oh, okay. We have it. Sorry. So if we take the log of this, if we take the log of this, it's getting worse now. Maybe I should just shout and take it off.
You could, for us, we could take it off.
But maybe the people in the back, I don't know.
Well, it's online.
Oh, yeah, of course, right. Okay, well, anyway, hopefully it won't be too bothersome. So if we take the log of this to discuss the effective action, it has a log of EI minus EJ, which has a singularity as they come together, and that will always be this smooth thing, which is just a Fourier transform of the thermal correlate, doesn't have any singularity there. And so then at some point we get to this Thales time. And this tends to be a very long time scale, at least of order the entropy or even exponential in the entropy. Okay, so that's much, much longer than this time scale. Now,
What is it? Which, the two are quite different.
yeah, those two are quite different, and I think, well, a little bit depends on the definition of the Thales time, because you have to
S is
say,
order log,
S is of order N is S. Okay.
right.
Right. So the point is, when you say that the thing should look similar to the ramp of the random matrix theory, how similar? And so because this thing grows logarithmically, you have to be pretty close, so when is the logarithm big enough to fit your epsilon? Okay, so we'll have to define the Thales time more precisely than it is often defined in the literature to define the time precisely.
But it's usually order entropy, right?
It's usually order entropy, right? Yeah. So then that corresponds to this term looking like log S bigger than this term. Okay. So that's the.
For the Thales time, just of a Gaussian matrix model for the energy?
Well, after the Thales time, you can just forget the other operators. So it's like a one matrix model for the Hamiltonian. And you can forget the fact that the other operators correct the eigenvalue interaction. And then, of course, in that region is where you have, the higher genus corrections become important, because by then the correlators and partition functions have decayed a lot. So we have higher genus. And it's important, of course, they contribute at any time, but here they kind of control the answer. That's the story of the ramp and random matrix theory and so on. And eventually, even, right. And then, at some ultra late time scale, like, e to the s, we might start to see the individual levels that they're not random, that they're specific numbers. So at this time scale, we sort of have exact.
Probably e to the s would be.
Well, no, the time scale of e to the s, you still.
You can begin to separate.
Maybe you're right. Okay. Yeah, that was too extreme. Yeah. You begin. Yeah, that's it has to be like bigger than e to the s. Yeah. Then you'll see the exact levels. And so at that point, you don't expect any matrix model to be correct anymore. So the range of this kind of model is very long. It's like all the way from there to there. And it encompasses many other sort of ansatz for microdata in thermal systems, but it kind of repackages them in this nice way. So that was basically the idea.
What do you mean by matrix model doesn't work after that? I thought that's just the whole time.
Well, if we have a specific system that's not the disorder average, then you have some specific energy levels, and you don't have a smooth plateau. You have highly erratic behavior, which knows about the individual levels. But yes, if you kind of average the quantity, then you can push it further. Yeah.
Could you comment again, if the UV is a strongly coupled CFD, what is the matrix time in that case?
0, it's just immediate, because the thing is conformally invariant, so it's kind of in other words, if the theory is a strongly coupled CFT in the UV, then there is no basis in which you know the operator O is some simple expression. It doesn't exist such a basis, right?
But if this holographic CFT, for example, I would assume from the Bach picture, it is when the particle falls to the near horizon region?
That's not even necessary, yeah. So this kind of matrix model captures the physics even broader, yeah. That's not required. Okay, and one of the things I emphasized was that Gaussian ETH corresponds to fully scrambled. I said it already. that is that the out-of-time order correlators are 0. And the opposite regime is what I call thermal mean field theory, where we have correlators that are just sum of Wick contractions. That's a system that doesn't have scrambling, right? So the physical system is somewhere in between, right? We're usually interested in some time scale in between. But we can write a matrix model for thermal mean field theory. That's kind of the starting point. And then one could add corrections, so we could kind of expand from either side. We could start here with the Gaussian model plus corrections. So you're starting from fully scrambled and putting things back, or you could start from thermal mean field theory and then add corrections to that. And in thermal mean field theory, there's a constraint, which is this fact that the operator commutator is a function only of the energy. It's not a general, non-trivial operator, and if we pick operators at random, they won't obey such an equation. And one could translate it into energy eigenbasis. If you do that, this PEI means the projector onto the microcanonical window with energy E1. And then we put our operator, then we put another projector here, where omega is a parameter. E1 and E2 are going to be parameters. So this is a piece of the operator product of O with O. Initial energy E1 and final energy E2, and we put some projector in the middle. And we could get this by taking the two-point function in time and doing a Fourier transform, which picks omega. If we wanted to get to the thing in real time, we integrate omega with a Fourier factor. And then there's another term, which is the other order. And when you have the order the other way, you get minus omega in the middle instead of plus omega, because you switch which one is at t and which is at 0. So we get a difference like that, and that thing will be equal to, I'll put it up here, something which is diagonal in E1, E2, because I get the product of the two projectors, and then the thermal green section. Where beta is the inverse temperature associated to E1 thermodynamically. Okay? So that's the constraint you get in thermal mean field theory, and the matrix model basically imposes this constraint by taking the square with a very large coefficient. And that turns into a potential of the type written over there, which we can, it's easiest to write it if we rescale the operator by its own two-point function. This g hat was the thermal two-point function in frequency space, where I just took out a factor of e to the beta omega over 2 for convenience. And if I define a rescaled operator, if I define a rescaled operator R, which is related to O by energy-dependent rescaling, okay, where here E is the average of these two energies, omega is the difference. This is the thermodynamic relation of temperature and energy. And then the potential, which I now write as a function of R and the energy, is given by some big coefficient. This time is not that n. Let me call it K. I'll tell you what K is in a second. And here we have, write this. So A and B, I call it I and J, A and B. So I and J are energy levels, and then we have here some specific function. Again, these depend on I and J, the way I said. This cinch comes because of the factors of e to the minus beta omega over 2, okay, which are kind of part of the KMS relation.
So can you explain once what is this PE?
Right, okay, so the point is that we're working in the thermodynamic limit, And there's the usual thermodynamic relation in which the temperature is the derivative of the entropy with respect to the energy, and that defines beta. Okay. And that's what this function means. And when I write here E, this E is the average of these two E's, and the omega is the difference.
Sorry, I was asking about this PE.
Oh, PE. Oh, sorry. I thought I heard. I didn't hear it. Sorry. PE means the projector onto a microcanonical band with energy E1 and some width.
Okay. So that means this omega in that first line is effectively 0, since you are projecting effectively E1 is equal to E2 since
Yeah,
you have
that's
two projectors,
that's true.
E1, E2.
No, sorry. I mean, in this formula, this omega is this parameter, which is a parameter.
Oh, it's not 1 minus E2.
And then this is, in this formula, this omega has this. Yeah,
I
sorry,
see,
that was
I see.
a little
Can I interrupt real quick?
Oh, yeah.
And Lloyd is going to just put it down a little bit so it's a bit further from now.
Okay.
That's all the problem.
We tried that, but maybe it's even further, and then it will be good.
Okay.
Good, okay.
1, 2, 3.
1, 2, 3. I mean, I still hear a little crackle, but it's not as bad. Okay.
Maybe a little bit better.
Okay. At some point, maybe the microphone is not going to be doing anything.
I'll take it out.
Okay, good. Can I continue? Yeah, sorry, that was maybe slightly confusing, but the omega here is this parameter in this one.
Okay.
Okay, so anyway, there's this kind of piece, which is like a 2-point function. And then there's a quartic piece, which I'll just write schematically because I put it on the board the last time. I see it still crackles. So which is sum over 4 levels, and then we have Rij, Rjk, Rkl, Rli, just the cyclic product of the matrices. And then there's a factor here which looks like the uncrossed Wick diagrams minus twice the crossed Wick diagram. And this thing is just, when we rescale to the matrix R, this is just a delta function that sets this energy equal to that one. This is supposed to be a Wick contraction of 4 points. So, I mean, this is delta of EI minus EK divided by the spectral density of EK. This is the same thing for JL. And this thing is the thing that sets this frequency equal to that one, which is delta of EI plus EK minus EJ minus EL. So that's the structure. And one can check that with this matrix ensemble, it reproduces the correlators of thermal mean field. Now, it might be a little surprising that a free theory turned into a very non-free matrix model. This model is highly non-Gaussian. This term is not small. It changes the answer a lot. If you deleted it, you would not get cross diagrams. But the simplicity of thermal mean field theory is encoded by the fact that this model is integrable. So if you look at this quartic coupling, if you take 2 quartic couplings and put them together, well, since this is just a delta function that says this frequency equals that one, if we put this diagram like this, it says this equals that and that equals that, which is just the uncrossed diagram.
Yeah, when you say it reproduces thermal mean field theory, you mean in the black hole phase or in the...
Oh, so
Or in plasma?
this is more, here we just took the different phases correspond to different possible values of the thermal 2-point function, and whatever it is, we write the associated term. So,
But these are not known, I would say.
in general, it would not be known, right? Of course. So here, I kind of imagine if somebody knows the answer. I'm just trying to reproduce. I'm just asking if you know the correlators, what are the ensemble of microdata that we reproduce? We could try to go in the other direction later, but so far we're solving that problem. That's what the ETH is about, right? You don't compute the 2-point function from the ETH. You kind of know the 2-point function, and then you say, well, that's what it would have come from microscopically. Well, maybe somehow you... We'll see soon in the JT case that there's this sort of you kind of can build a set of rules for the constructing the matrix model that in a way could let you go the other way, but okay, but you have to first learn how to construct these rules. So, anyway, it obeys this unlacing rule and also a Yang-Baxter equation. So if I cross the lines like that, this is like integrability in the standard sense, and that's why, although it's a non-Gaussian two-matrix model, it's solvable. In fact, we started with the solution. The solution was free field, so okay. Because of this unlacing rule, if you actually go and try to sum the diagrams, it looks like you get divergences because, no matter how many bubbles I add, I always get the same answer. And so if one wants to really define things carefully, one should regulate this model a bit so that you don't have this exactly and then take the limit at the end.
How do you do that?
Well, this basically corresponds to replacing here these delta functions by a thickened delta function. And so that's the regulator in this case. So it's because when we have this thing with the delta function, delta squared will appear in some quantities. Okay?
But then you preserve.
That will not preserve. Well, actually, there exist regulators that preserve the Yang-Baxter equation. They just modify this, of course. Of course, you can't regulate in theory preserving this, because this is why when you sum the diagrams you get a divergence, because they all give the same. Okay? But so the goal of regulating is that you replace this by something else, but you can keep this. We'll see in the JT case that this Q-deformed theory does exactly that. Now,
So this allows you to compute correlators of O and the energy momentum tensor in some thermal state.
exactly.
But I thought like even from large N we don't know anything about these things. Like mean field theory predicts something about correlators of O, because you can use weak construction.
Right.
But when we have O's and T's at the same time, nothing is known to my knowledge.
Well,
Or T's the energy line.
Yeah.
yeah. Well, in the JT example, I'll tell you, we know the answer because it's holographic.
Yeah.
So, yeah.
But you only inserted the correlation function for O as a constraint, not correlation function for H.
Yeah, and that's right. But soon I will also discuss correlation functions with H when we discuss this JT gravity story.
Another question. So in this picture, in tensor picture, when do you class this model starting from where?
Well, all the way from here to here. So it will not tell you the exact levels, and it will not tell you about some very short timescales where the theory looks free in some original variables, but anywhere else, this kind of model you can find the potential so that it will work. That's the
So
class.
you find the chaos exponent without doing anything but the super?
No, of course not. I mean, you take the correlators as an input. So this is again, we take the correlators as an input, and then the output is supposed to be the statistical ensemble of the microdata. We're not computing the output of the true exponent.
It doesn't look true because we know correlators of O, but when we have O's and T's, we cannot use weak constructions anymore. I don't know.
Sure. So this thermal mean field theory was just one example, right? That wasn't meant to be all theories. That was the case where the correlators are very simple.
Okay.
So then we can, so just an explicit example where the correlators are very simple, then we can work out what is the V. But if we have another example, we'll get another V. And if we don't know the input, then we don't know the output. Okay? But the more interesting example is this JT with matter, which is kind of the improvement of thermal mean field theory to include the energy exchange. And so that's what I'm going to do in 2 minutes. All right, okay.
So sorry,
yeah.
when you say you can trust the theory after a matrix time, you mean, say, if I want to match the observables,
Right.
the higher point correlations you didn't put into as constraint, do you still trust it, or?
You need all the higher point correlators.
Okay.
Of course, if we say it's thermal mean field theory, we said all the correlators. Okay? And when we'll discuss JT coupled to matter, we know all the correlators. But you'll see, yeah. Okay. Okay, I think that's all I really want to say here. Okay. Good. Let me turn now to this JT story. So thermal mean field theory is not very interesting, as has been just discussed. It's just, free Wick contractions of one operator. A more interesting example where one could apply these ideas, and maybe that was kind of the motivation of this whole business, is if we take a holographic theory where we know the dual, then that's also a situation in which we know the correlators, and we can try to see if we reproduce them from this kind of matrix model. And in that context, we're going to start to get some outputs that we didn't put in as inputs. One kind of output that you can get from this is what the matrix model predicts at higher Js. So we will construct this model for JT with matter, starting only with the disk amplitudes, like the leading black hole amplitudes. But the model will automatically give the correct answer for all higher Js. Now that's similar to what happened in the story of Shankar-Stanford. So we can say, in this SSS story, it's like, of course, there's the old matrix models, which relate integral over some matrices to 2D string theory or 2D gravity. A specific example is one where the worldsheet theory looks like JT gravity. JT gravity is, defined by a bulk action that looks like it has the 2D metric and the 2D dilaton. And the most important term in the action is this, where the dilaton is a Lagrange multiplier that just sets the curvature to be constant. So the solutions are locally trivial. They just look like low ADS2, but there's some non-trivial dynamics in the boundaries. So it's a very simple theory of gravity, in that sense analogous to 3D gravity, pure 3D gravity. And then you will put some boundary term in, so SSS discussed this theory of pure kind of topological gravity, in that sense very analogous to the minimal string worldsheet theories. And they relate it to some matrix model. In order to get JT gravity instead of minimal string theory, it's a double scale, minimal string theory is also double scaled, but it's a very specific potential. And these models are double scaled in the sense that the range of the spectrum of this matrix is infinite. Whereas in the standard Atov scaling, it will be a finite range. And there's a coefficient here that we dial to infinity as we take the rank of the matrix to infinity. In the standard Atov way, A proportional to n, the size of the matrix. And you can think that in these matrix models, the input is, but one of the sort of the new ingredients of SSS is that this matrix here has the interpretation of the Hamiltonian of the dual quantum mechanics. So if we insert observables into this is just the partition sum of this ensemble, but if we compute expectation value in this ensemble of observables, like trace e to the minus beta h, this has the interpretation of the sum over topologies in the 2D JT gravity where the boundary has length of beta. So the pictures it's associated to is some nearly ADS2 boundary with length beta, and then it could be filled in with a disk, or more generally some blob with a handle on it, and one takes the sum over the disk and things with arbitrary numbers of handles. This corresponds to the genus expansion of this matrix model, which now gets interpreted as an e to the minus s expansion. Okay, or e to the minus s naught, where s naught is another parameter that appears in this theory in the following formula, where this is just the Euler density, so this is literally counting the number of handles. Okay? So that was the story of SSS, and you could say that the input is just the disk spectral density. So in other words, the spectral density that you compute for JT gravity, if we look at the disk, which is the Euclidean 2D black hole, we extract the spectral density of these JT black holes. That's the input which fixes this potential. We can't really write the potential as a function because it's double scaled, right? So there are parameters that go to infinity, such as the Topf scale, it's double scaled, and the spectral range is infinite. The disk spectral density in this story, the genus 0 spectral density, looks like a sinh function. And so that's the input, but then the sum over topology is an output, and it agrees with the sum over topology in JT gravity. But that agreement is, in a sense, the same miracle as in the old matrix models giving sum over topology again. Okay?
I'm sorry,
Yeah.
can you repeat what is the significant difference between the old matrix model and this matrix model, if any?
Right, right. So, I mean, I think the one new fact, which is not a difference of the models, but a new fact, is that you get a clean interpretation of the matrix. So this matrix is the Hamiltonian or the dual quantum mechanics in the sense of 2D ADS-CFT.
But apart from...
So I think that's the most important new ingredient, and then it's a specific example, if you like, of those matrix models.
referring to difference in the for instance, if I remember correctly, in the old story, you do not expect to see black holes. Here you do expect to see black holes, so somehow one would expect significant differences.
No, but there's a change in interpretation here. So here we say a black hole, we mean the world shape. There's no space-time here. There's a world-shaped black hole. It's a world-shaped black hole. That, of course, you always have, because it's the analytic continuation of the disk. Okay. Yeah. And here we do not take the space-time interpretation. Yeah. Well, that would look exotic. The space-time interpretation would be very exotic from the point of view of JT gravity. And in fact, if we thought that this is a toy model for higher D ADS-CFT, in higher D ADS-CFT, there isn't an ensemble of Hamiltonians, fundamentally. Specific Hamiltonian, and writing an ensemble is an approximation to some pseudo-random aspect of specific Hamiltonian, and then that means that the target space is destroyed. Right. Somehow the target space picture, you really need this to be an integral, not a sum of delta functions. Okay. So somehow the UV completion in that sense, the non-perturbative completion of the genus expansion, which gives you the target space in matrix models, is not the non-perturbative completion of the genus expansion that you expect in higher the ADS-CFT when there is no disorder in the Hamiltonian. Okay? Good. Yeah.
I have a very elementary question. I mean, holography came from string, and you had to have a 10-dimensional bulk that is drawing from some boundary feature. Now you take directly ADS2 with no additional space-time direction, and you map it to quantum mechanics.
Right.
Where does it come from?
Yeah, that's a great question. I think the real answer is whenever at the end of the day, when you sum the genus expansion, you include everything. If you still end up with an integral here, you're in a bad theory. Okay, the theories where you get at the end of the day an integral are not good theories of quantum gravity on the world shape as its own story that's the end of the story. Okay? Then you need to pass to some target space, and you kind of have to reinterpret this. If we were doing higher D ADS-CFT, then this H is the H of n equals 4 super Yang mills. At the end of the day, these are 4D geometry, 5D. These are ADS5 times S5 geometries. And then at the end of the day, when you sum it all up, the integral goes away, right? It will be localized to a specific H. That is very special. It requires the theory to be special. If we pick, so JT gravity is UV complete, but it's not holographic. It's not holographic, and the sign of that is if you take the sum over topologies, it gives you a thing with an integral, That's in the swampland, if you like. Okay? So if we want to say, how can we keep modifying the theory in the bulk so that eventually this integral gets localized after you sum everything, then we will need the whole string theory here. That's where that will come in. It looks very indirect because you're kind of expanding from the opposite. Because somehow this is a, you know, we can think of this as starting from like the IR effective theory in the bulk. Right? So then, but actually I'm going to come back to those issues a lot in the rest of this lecture and in the next one.
So are you saying that world-ship gravity is the swampland in general?
Right. If you take that to be the whole world, it's not the self-contained system. Right. You know, it's not the self-contained system. It's a system that lives on an object embedded in something else. You need the something else to make it consistent. That's what I mean. So, yeah. Actually, maybe I would say this now, even though it's a little bit out of order of what I was going to present, but let's suppose we try to play this game in higher dimensions. Then we will be discussing random CFT data. This is something that some people have been working on recently, and myself and some others. It's not a fully finished story, so I'm not going to try to describe it in detail. But we would say if we have, say, a higher DCFT, maybe even a 2D CFT, what is the data? The data is the dilatation operator, which is graded by spin. The Hilbert space is graded by spin now. That's a technical difference, but there's a dilatation operator, and then there's a tensor, right? So we usually write dilatation operator with one index, but that's because we diagonalize it when we go to energy eigenbasis. But to be more like this, we will think of it as a matrix. It is a matrix on the Hilbert space. And then the structure constants are, you know, a rank 3 tensor. And we can imagine that we should pick them all at random. And we can say, suppose somebody did some computation in pure 4D gravity, an approximate calculation of the, you know, 80 is Schwarzschild black hole, 80 is for Schwarzschild black hole. And then we interpret it as thermal correlators in a CFT3. That will give us some constraints on this data. And we can say, well, what is the ensemble we get, which is consistent with whatever input data somebody computed. Okay? And then, of course, if you don't compute much, you'll get an ensemble. But in CFTs, there is a constraint which you do not have in quantum mechanics. In quantum mechanics, any Hamiltonian is good. Any instantiation of this ensemble is a consistent quantum mechanics. You can't stop me from discussing some Hamiltonian. But if we have a higher DCFT, we are not allowed to just pick these arbitrary. They will not obey locality of CFT, which is the same as the crossing equation. Right? They will not obey the crossing equation.
That's okay. Couldn't you have a kind of a discrete ensemble?
You could have a, yeah, okay. You could have a discrete ensemble, but yeah. You can have a list of CFTs, but in the list of all CFTs, so how much data is there in these? Well, the amount of data in this is, you know, the total number of, the dimensionality of the Hilbert space, which is infinity really, but if we look up to some energy, it will be some e to the s cubed. That's a huge amount of numbers. The discrete collections or, you know, modularized spaces will not have, you know, this number of parameters. They will have, you know, some small number, at least we don't think so. Unless we think they're, you know, e to the 3s, well, e to the infinity CFT, you know, that seems very unlikely. Right? But I don't know. Right? What one would like to do here, and it's very much in the spirit of what we discussed in thermal mean field theory and what I will discuss in a second about the JT with matter, is you could take an ensemble where you try to impose the constraints. So we can say that we take an integral over this matrix and this tensor where what should the potential be? Well, there's a very natural guess. It's the square of the crossing constraint. So we can put exponential minus some big coefficient, crossing squared, summed over all external operators and cross ratios. So if I sum over all external operators and all cross ratios, this quantity is positive, and is 0 if crossing is obeyed. And so I can try to study a model like this. And it turns out if you do that, it has a structure, let's say we're in 2D CFT, it has a structure, then there's also modular invariance, we do the same, and it has a structure which looks very much like 3D gravity, like the sum over topology in 3D gravity. And now it's much more non-trivial whether in the sort of double-scaled limit this model exists or doesn't exist, and it's tightly connected with whether when you sum everything on the bulk, it's a good theory or not a good theory. So, but I can't say too much more because we haven't gotten that far yet in this, but yeah. Okay, but somehow this is maybe where it would go. And in fact, in a model like this, you're kind of going also in the forward direction. You know, this quantity doesn't know about the theory. It's universal, just a feature of consistency of conformal field theories. But somehow this model knows all conformal field theories. It sounds very silly, right? I just suppose the constraints. But you know, this thing is extremely specific matrix tensor potential. It's not something abstract. You know, well, some 6J symbols, I could write it down, and one can sum diagrams in it. It sounds like you could use it to compute the thermal correlates. Okay, but we won't go to that because that's not a done deal. Okay, let me return to the story. So we're going to try for now something less ambitious. We're just going to put some matter here. Okay, so that's nice because in this JT story there's no propagating degrees of freedom, just like in the minimal strings. Now we add some propagating matter. The story is much richer. This gives us another operator, the boundary, you know, the CFT, or the quantum mechanics dual of this matter field. And the simplest choice is to just pick minimally coupled matter. So we take the matter action to be where you can put in the indices. Okay, some massive scalar field. And it has an associated dimension of the dual operator given by the usual ADS formula. And now we can compute the thermal correlators. Now, luckily, this job is done. In JT gravity, one can compute these correlators exactly, especially the level of the disk. And the answer is that they look like the sum over diagrams that look like Wick contractions, but the number that you assign to the diagram is not just the Wick contraction. It includes the sum over the boundary graviton exchange. You know, all the ladder diagrams where you exchange the boundary graviton, which looks like a Schwarzian mode on from the boundary point of view. So if we're computing, I don't know, a 6-point function, one kind of diagram, you know, this is, oops, I need 6 points. This is an example of a diagram, okay? So this is just a free propagator. But here, when the lines cross, we put the 6J symbol of SL2R. That depends on 6 parameters. 2 of them are just the dimension of the dual operator, and the others are the 4 energies. Actually, it's more convenient to write things in terms of the square root of the energy, it turns out. So maybe I'll define S to be the square root of A, and then, you know, we have these 4 regions. We get S, you know, I don't know, 1, 2, 3, 4. We get S1, S2, S3, S4, and this bracket means the 6J symbol of SL2R. The 6J symbol is a group theoretic object which tells you how to sew together 3 representations. So these are the rules for computing in this JT gravity coupled to matter theory. So basically, if we replace the 6J symbol by the delta function, which says that this frequency equals that and this one equals that with nothing else, that's the trivial scattering. That's thermal mean field theory. And in this case, our thermal mean field theory is more specific. It's this CFT1 generalized free field where the operator has dimension delta. Free fields in ADS2. But then when we include this factor, it resums the gravitational exchange. Okay. So now we take that as the input, and again, this defines not only the 2- and 4-point functions, but all higher point functions.
Resum, you mean to all orders in G Newton?
Yeah.
Okay.
Yeah.
In JT gravity, there are a lot of methods.
Sorry?
There are a lot of methods.
A lot of masses.
SYK.
Oh, and SYK. Yeah, well, we're not doing SYK. Yeah. I mean, it might have some, it's a piece of SYK, but it's not the, yeah, the full SYK, you have a matter field for every product or something. Yeah, there are many matter fields.
So Daniel, this resembles loop diagrams, all the loop diagrams, like of JT gravitons or something.
That's correct, yeah. Yeah, it resembles all the loop diagrams. And the matter loops here don't do very much, so they're, because it's just Gaussian, but also the actual determinant is a trivial thing. So it doesn't, if you were to compute this, well, the matter determinant in the disk topology is a trivial thing. So it's, it just has a cosmological constant, which is like the area, computes the area of the disk, and then a topological term. The cosmological constant piece can be reabsorbed into a redefinition of the Newton constant. Okay? And the other term renormalizes this S0 term. So you can eliminate this determinant. It doesn't generate any new structures. And so the spectral density here is the same as in pure JT gravity, up to this definition of parameters. That's very special to JT gravity. That's not generic. And higher genus is different. And one of the things that I will tell you is that the matrix model reproduces the determinants of higher genus. So it kind of, once you input the disk, it gets everything else. Okay. Well, we already knew that that was true for the kind of topological gravities, but maybe it's surprising that it works even when there's propagating matter. Now, this theory, when we include higher genus, can have divergences in the integrals over moduli, because if I have, a very narrow, let's say even the simplest kind of thing, like this double trumpet, if I need to integrate over the length of this circle, and this looks like, when B is very small, it's a very high temperature regime for the matter theory down in this throat, and I will get a thermal divergence. So when I say that the matrix model agrees with it, I mean it reproduces the divergences in exactly the same way. And there are, so if I do a computation where instead of computing this quantity, I compute the quantity where I fix the B, I get the same answer. If I do the integral, I get infinity, but the theory gives me infinity. If I modify the theory, I will have to modify the matrix model, and I will tell you a matrix model which everything is finite also. So the maybe I'll just let's see. If we ignore the fact that the matter lines crossed, okay, then could have a Gaussian matrix model. That will be the case where the out-of-time correlator vanishes, and we just have the Gaussian matrix model. And then the only input would be the two-point function. That would correspond to a quadratic potential that looks like this. Just to write the formula once. So that's just the appropriate transform of the JT two-point function. And the plus and minus means the product of 4 terms, each with each sign. And this is some gamma function. So this is the matrix potential for the ETH, kind of the Gaussian in O ETH approximation. But we want to allow the lines to cross. So that means that the model has to be at least quartic. And it turns out that quartic is good enough. You don't need anything higher. And in fact, in this theory, although it's not just free Wick contractions, there's still a constraint. The constraint is a little bit more complicated to write, so maybe I'll let you read that in the paper and just explain why there is a constraint. The explanation is when you reorder 2 operators, you do not get a random new operator. You get the same operator as before dressed by the Schwarzian, which means particular functions of the Hamiltonian.
What do you mean dressed?
Yeah. So let me actually write the constraint. Let me write the constraint, and maybe it will be kind of clearer. So we can write it in the following way. So I have OAB, OBC, the product of my two operators. And then let me remove this gamma factor. So by gamma delta AB, I mean this expression with the product of the four terms. So I have this object. And now, if I had been in thermal mean field theory, the constraint that says that the commutator is a C number, or is a function only of the energy, would have said that this object times delta of SA minus SC over rho, which is, I factor out a factor of e to the s naught in rho, because that's just an overall number, rho of SB minus, sorry, SA, delta of SB minus e to the s naught, rho of SB, where again, S is the square root of the energy, just makes some formula simpler. So this thing is the commutator in energy basis, and that would be equal to a specific function of the energy if we were in this generalized free field situation. But because we have the gravitational exchange, the constraint looks not like this, but rather we get here the 6J symbol with these parameters. Okay. And this thing is summed over B, the intermediate energy. So it says that when we take the two operators with a definite energy projector between them and we reorder them, we get an integral over all energies in between with this function. Okay, so in other words, if we look at this cross diagram, we have here SA, SC, SB, SD. Well, before, in thermal mean field theory, this thing is going to equal SA plus SC minus SD. Well, the squares of them because of the energy. Because it just says the energy is conserved through here. But now, when we reorder them, when we have the gravitational exchange, we get a whole integral over the intermediate energy. Okay. So that's the distinction. And if I, yeah. So this thing is equal to sum over B, this same expression, and now something which is just a function of the energies, delta SA minus SC over the spectral density. Okay, so this is the exact expression of the constraint here, but it's morally similar to the constraint of free fields, except that now we have this sums. And if we take this object, it also obeys an unlacing rule and the Yang-Baxter equation. Exactly the same. It has this property, that this is a true property of the JT amplitudes was already observed. It's related to the fact that these sum over chord diagrams don't depend on, they only depend on which line you contract with which. You can cross them and you get the same answer. Okay? And it obeys the Yang-Baxter equation. So it's again an integrable kind of structure. And the matrix model takes the form of this constraint. We put this onto the left-hand side equal to 0. And then we take the square of that, summed over all coefficients, and that will include terms which are quartic in the operator from this thing squared, as well as the quadratic term, the cross term. And that's actually the entire model. So the So we have an integral over H and O. If we bring this to the other side, let's call it MACB. We get sum over A, B, C, MACB squared, and if you expand that out, that's a single trace thing, which is quartic and quadratic, and then there's a constant term, which you just discard.
You don't need to put the coefficient to infinity.
Oh, yeah, sorry. There's a coefficient here. And exactly, we need to take the limit that this coefficient goes to infinity. So it imposes this constraint. And again, the fact that there's a coefficient that goes to infinity is not too surprising because of this unlacing rule. Because you have this unlacing rule, if you try to sum the diagrams, all of these multi-loops give the same answer, so there's some divergence that has to be canceled by something else going to infinity. Another way of thinking about it is if you started with the Schwinger, in a sense we're starting with the answer here. We know the amplitudes we want. So we can write the Schwinger-Dyson equations for suppose we wanted to compute what is the quadratic and quartic in O couplings. And if we assume that there are no sixth and higher order in O couplings, then we can write a closed set of Schwinger-Dyson equations for the couplings and the amplitudes. Here we know the amplitudes, but because the amplitude obeys this rule, you'll get a divergence in the Schwinger-Dyson equations tell you that this coefficient goes to infinity. But to do it very carefully, you have to regulate a little bit, okay? So you need to replace this delta function here by some smoothing thing. And there's another little wrinkle, which is that the 6J symbol, it grows. The terms that you get with this grow too much at high energy. So there are diagrams that look like this, which are divergent. But if you regulate them in an appropriate way, they're sort of removed by a counter term. And in the Schwinger-Dyson equations, this kind of term actually drops out, interestingly enough. Yeah.
So then clearly this matter action that you added on flat space-time is integrable, but you claim that if you couple it to genetic gravity, it's still an integrable model and there are infinitely many conserved charges?
Is the bulk theory integrable? Well, the correlators are known. So in that sense, in the sense of integrable as solved, it's not only solvable, but I wrote the solution, but I mean, other people worked the solution out, right, on the gravity side. It's not I'm not sure if it's integrable in the usual sense, but, the amplitudes do obey Yang-Baxter equation and the unlacing rule, so in that sense, but it's a chaotic set of correlators in that the function that appears, the 6J symbol, has some exponential growth in time built in, when you go to the real-time basis, you find some exponential growth of out-of-time ordered correlators, so it's sort of both chaotic and integrable, but by different definitions, right?
But ordinary law, you would say that they are not integrable because they have this chaotic behavior.
Right. So that's why I hesitated to answer, but it's a solved set of correlators. Okay, so now, so far these are all things kind of on the side of input. We just said somebody smart solved JT gravity coupled to matter at the disk level, and then we rewrote it as this kind of matrix model, so it tells us what is the microscopic statistics of the theory. Now, here again, there's no constraint of consistency on the quantum mechanics side, right? Any Hamiltonian, any operator are good. We can pick any random instantiation of this ensemble, it's always good. In that sense, we can take this as a version of the story of HPPS, so that was the statement that if we are studying ADS-CFT and one has a bulk theory written in the G-Newton expansion, G-Newton perturbative expansion around free fields in ADS, that gives a perturbative solution to the bootstrap equations of CFTs, the consistency relations of CFT, in a 1/n expansion. And any bulk effective theory maps to good perturbative solution of the bootstrap. And now we know that there are some bounds on the Wilson coefficients. They cannot be too far from the values that would be dictated by dimensional analysis for irrelevant operator coefficients. So we're working with Stella and many others. This is a little bit of an example, an analog of that for the thermal correlators. So if we will take any effective theory in ADS, we find the ADS black hole solution, we work out the thermal correlators at a finite point number in the perturbative expansion, then we can deduce the we can find a collection of dimensions of the black hole microstate operators and three-point function of light operator O and two black hole microstates, the two indices of the matrix, such that it's consistent. But now we don't even get specific ones. We get a whole ensemble of consistent things, but we don't get any strong consistency constraint. Any effective theory is good. Okay, we just take the correlators and produce this. To get a constraint, you have to do something like what I had written before on the board when we discuss the crossing even of heavy operators. That's when you really get some strong constraint that we think nails down the answer. That's why we don't have e to the s cubed degrees of freedom of CFTs. By degrees of freedom I mean changing the theory. Okay. Good. Okay. So now we can try to take this story at higher genus, and now at higher genus everything is going to be in a sense an output, and there are many kinds of diagrams that one could compute. So first of all, there's just a fact about the gravity amplitudes, which is kind of interesting. I think was not known before, which is the same rule with the 6J symbol also computes the gravity amplitudes at higher genus. So just as an example, let's suppose we have the pair of pants where we fix the lengths of these three geodesics. This is a hyperbolic pair of pants that has the constant negative curvature metric. And then imagine we were going to compute the matter determinant on this manifold. We could try to do that using the quantum mechanics approximation. But actually the quantum mechanics approximation can be solved exactly because we have manifolds of constant negative curvature. So we find a geodesic, like here's an interesting geodesic. Okay, so it's kind of a figure-8 geodesic with a self-crossing. It doesn't look very geodesic-like, but there's geodesic with this homotopy type. So we take this trajectory and then we can do the perturbative expansion around it. But because the manifold is constant negative curvature, we can just solve it. It doesn't depend on the rest of the manifold. That's called the Selberg trace formula. So the fact that the determinant of the Laplacian on hyperbolic manifolds with constant negative curvature can be written as a sum over all the geodesics of something specific that only depends on the length is the Selberg trace formula. This gives a particular contribution. And now the rules here say that we should have done this computation by inserting a 6J symbol here, and then an appropriate factor that instead of fixing the energy in this leg, we fix this length. So that's a functional transform. It's a Fourier transform, turns out. So this should be related to something given in terms of the 6J symbol. Indeed, it works. Okay. So this is like a figure-8 where we do integrals over the energies S1, S3, and S2 with cosine of S1, B1, etc. And then here we put the 6J symbol. That equals that. So, and I mean, we actually didn't prove this statement, but presumably it's true at all higher genus and arbitrary crossings and so on. And the matrix model reproduces this quantity. And so it reproduces the Selberg trace formula on these higher genus manifolds. And if I had a correlation function at higher genus, then there'll be lines from the boundary as well as closed loops coming from the determinant. And every time they cross, we get the same 6J symbol. And that's what the diagrammatics of this matrix model produces. Except there's one small wrinkle. Okay, but this wrinkle is very interesting. So So the small wrinkle is the following, and it has to do with the fact that there are divergences in this model. So it's kind of the following. Let's suppose we wanted to compute the simplest thing, which is the double trumpet, the determinant on the double trumpet. And we want to look at the contribution. We have just one line, one matter line here. Okay, so we want to compute that thing. Now, in principle, in the matrix model, this is about the measure. This depends on the measure for the matrix integrals. So if we would say that we rescaled the matrix by a function of energies, we could change this answer. So a more universal thing is if we compute the correlator with the cross line. So we insert an operator here, and then we have one crossing, and that loop is in the back. Okay.
This story about the Silberg formula, that was in some large mass limit?
No, it's exact.
Because you only get this approximation with geodesics in a large mass limit.
No, so the point is that because the manifold has constant negative curvature, the whole, so we're doing the perturbative, you can resum the perturbative, basically it's one loop exact. It's one loop exact, the quantum mechanics is one loop exact, and so then you just solve it. Yeah, okay. But that depends on the manifold being 2D constant negative curvature. That's very special. Okay, so we want to compute this thing. I put this extra matter line to make it not depend on the measures for the matrices. And we can try to get this diagram from a disk diagram by sewing rules. So we can open it up along the, like cut it open in the back. Well, maybe I should have used the other third color, whatever. Here's the blue line, these are the two boundaries, and this is the matter line in the middle. And when we do this computation, I will get another color. So the black lines are boundaries, the red line is the internal loop, and the blue line is an external particle line. So we could do this computation in the disk and then try to glue it together, okay? And then there are other kinds, so if you do that, you find it just works, okay? But when we do the computation in the disk and glue it together, when the full computation in the disk includes a propagator attached to this vertex, and in the disk we have two propagators. But when we glue it together, we're only supposed to put one propagator. So it's the usual story that when we cut open a loop diagram, we should compute the amputated diagrams and then glue them back, which is the same as the unamputated diagram with an inverse propagator for the thing that gets glued together, right? We don't want to put two propagator factors when it's glued in a loop. There's only one propagator factor. So when you do that with this single line, everything works just nicely. But then there are a next contribution to this answer, which is when we have two particles going around the loop. And when we put two particles around the loop, we can write a diagram like this, but then we can also write a diagram where they cross. These two kind of diagrams. And so again, we should compute the full amplitude. Now it's a 6-point amplitude. And glue it together with one factor of the inverse propagator. But now in this theory, there is a subtlety. The subtlety is because the propagator, we kind of glue it with the 2-to-2 irreducible propagator, which is the sum of two diagrams. But this thing is a projector, so if we were just doing free fields, we didn't have the interaction with gravity, this would simply be the exchange diagram, and the fact that this would be a projector is Bose symmetrization. This is the exchange of the particles, same step. Now we have the dressing with the Schwarzian, but it's still true that this thing squares to this. So this is still a projector onto a half-dimensional subspace. And so when we compute the full amplitude and then we want to make the loop by gluing it with the inverse propagator, we have an ambiguity. Because this has a 0 on things orthogonal to the symmetrized states, but so does this. So we get 0 divided by 0. It's not going to be what the answer is. Now, if we wanted the JT gravity with matter answer, we want to say that the non-symmetrized states don't propagate. Because we have a matter field that has both statistics. The number of states in Hilbert space is not, the order of the particles doesn't matter. So that's what's achieved by, so that can be achieved, but you have to take the limit carefully. What do I mean the limit? What I mean is to define this computation algorithmically from the matrix model, you should have regularized the answer so that it did not obey the unlacing rule. In other words, that this did not exactly square to 0. And then you do everything and take a limit. And if you take the limit in a certain way, you can get it to look like this in the limit. But there's a very interesting theory where the answer comes out to be different. So up to that ingredient, so if you take the limit like that, it reproduces the Selbert formula exactly. So that's one statement. But now we can do something different, which is there's this interesting theory called Q-deformed JT gravity with matter, which appears in the double-scaled SYK model. Now the double-scaled SYK model has matter with any dimension, because you make it out of product of A Majoranas, where A is any number. But here we're talking about not that theory, but the one with just one matter field. Okay. This is defined at the disk level by taking the same rules for computing the correlators, except we use the Q-deformed 6J symbol. And now the spectral, so there's a parameter Q, which you take to be between 0 and 1. And the spectral range is that the energies go between 0 and minus 1 over log of Q. And so as Q goes to 1, the spectral range goes to infinity again, but at generic Q, it's a finite range. So it is now a Toft-scaled model, not a double-scaled model. And in the Toft-scale models, there is no room for any divergences. And one can play the same kind of game and try to construct a matrix potential. But now it's much harder because although the correlators obey the Yang-Baxter equation, because Q-deformed 6J symbols obey Yang-Baxter equation, they do not obey the unlacing rule. But that's the whole point, because that's what regulated the theory, in a sense. So now it's not true that this is not just the unlaced diagram, but it's smaller, in a sense. So like the sum over diagrams is a geometric series and sums, but there are many other diagrams. And now, actually, we didn't manage to solve what the potential is for general Q in closed form, but you can work it out in a series expansion around different places, like small q. So order by order in Q, you can work out terms in the potential. And now there are not only quartic in O, but all powers of O appear. But we believe that if you take the limit as Q goes to 1, because the coefficient of the quartic thing goes to infinity, the other terms don't matter, they disappear. But it would be very interesting to read that maybe because the Q-deformed 6J symbol is somehow integrable, it's possible to solve for that potential in closed form, but we didn't do it. If we take this theory and we try to do these computations, we get a different answer. When, even in the limit that Q goes to 1. So first of all, when Q is not 1, it's clear that this is not a projector, right? This does not square to 1. This doesn't square to this. And so there are two eigenvalues. We're just talking about the Hilbert. So now we're just discussing the bulk Hilbert space of two matter particles in ADS2. And if we reorder the particles with this Q-deformed 6J symbol as the rule, the two orders are both non-trivial elements of the Hilbert space. There is not a null state for the one which is anti-symmetrized. It does not have overlap 0 with everything else. And so there are more states. And when you do this computation, you're basically computing the trace over the bulk Hilbert space, and so you get a very different answer. We could say it in terms of like the 1D state operator correspondence, right? We have, this is like the operator O, and these are operators O squared. Well, this is O, and O dressed with derivatives. And the dressing with derivatives is the gravitational, the determinant that you computed, and so on. Here we have O's with derivatives, but the order matters or doesn't matter depending on whether or not this thing is a projector or not. And so in a Q between 0 and 1, they don't go away. And in fact, one can show that as you take the limit, they still don't go away. So the Q goes to one limit has the states. And the spectrum is quite interesting. It's a Hagedorn spectrum. Because if we talk about operators with many, then we get all possible orderings of, we have like, del N O, and we have all possible orderings of them. They're all different. And that's just the number of words that you can make with derivatives and O's. And there's an interesting paper of Henry Lin where he studied this directly in Q-deformed JT gravity. Nothing with these matrix models, but basically derivative is like a Hamiltonian, commutative Hamiltonian, so you just make words made out of H's and O's, and the number of those words as a function of the total dimension, which is, here twice delta plus n plus m, has an exponential growth. So the spectrum is Hagedorn. And so this theory now does something kind of interesting. Well, until when should I go? Because I know I started late.
You started it as late, 5 more minutes.
Okay, thanks.
Real 5.
Yeah, real 5, yeah. That's perfect. So
So it's truly Hagedorn? It grows.
it grows exponentially.
Exponentially in the mass,
In the energy, exactly. And in fact, that's not very surprising because we can think of this counting of operators as kinks on a string. And the order of kinks on a string, the order matters. That's why the open string has this spectrum.
But then it can't be a quantum field theory.
Yeah,
Yeah. It shouldn't be.
yeah. And indeed, nobody really knows the bulk dual of Q-deformed JT gravity with matter, right?
And also, the cold amplitude has a similar truncation in the energy. Somehow is it related?
I'm not sure. Yeah.
What is the coefficient?
I forgot. I forgot. But it's just what you get by counting these, so it should be easy to. I mean, the combinatorics of counting these are very easy. So we could work it
Uniform
out.
just the matter, you don't uniform the JT itself, right?
Oh no, I think it's the other way around. We basically Q-deform the JT and not the matter or whatever. But yeah.
Why don't you do both?
Maybe we do both. I don't know how to answer this question. Well, maybe a kind of, there's something along these lines, which is, if we, here I imagined I was doing computations which were either where I fixed the energy or I fixed the temperature and times, but if I were, so that's like computations with trace e to the minus beta h, O's and so on, so I kind of treated h and O differently by the question. But instead I could, it's allowed to compute things like h to the a, O to the b, etc. Then the h and O are treated in the same. Those kind of correlators are computed in this double-scaled SYK, for example. That was kind of how they derived it by some chord diagrams, where now I draw lines for h and O on equal footing, and there are 3 kinds of crossing: H with H with O with O, and each of them just gives you a number. And by tuning those 3 numbers, you kind of cover the parameter space.
So you can't set any of them to be 1 at the beginning. You have to sum them to 1.
Yeah. The numbers are strictly between 0, well, strictly less than 1. Yeah. And then the things like the original JT with matter is some limit where you send one of them to 1. But yeah, so from that point of view, one is Q-deforming. You can't Q-deform everything. You can construct this matrix model for any choices of all of them. You can have 5 matter fields with 5 squared coefficients. And whatever. Okay, but all of them have this kind of Hagedorn spectrum, once there are at least 2 operators. Now, what was I going to say? Right, so kind of the basic object in these matrix models beyond the leading order is this double trumpet object. And in pure JT gravity, it's some kind of integral over this parameter b, which is this length, of a factor like e to the minus b squared over beta, roughly. And I think there's a b here. So I think that's the formula from the computations in pure JT gravity. But now if we have a matter field, we're supposed to put here the matter determinant, which is a function of b. And with ordinary matter, this grows exponentially. It's a thermal growth. This has some bad divergence at small b. What happens in this theory with this Hagedorn spectrum? Well, it says that this thing has a pole at finite b rather than an exponential divergence at 0b. So, I mean, the full function is something complicated, but there's a piece of the answer which looks like 1 over b minus b Hagedorn. Okay? And b Hagedorn doesn't depend on q, because it's just about the counting of operators. But the q deformation also does something else, which is it says that b is a discrete parameter. Because b was the Fourier transform of the square root of energy, and this range of the spectrum is finite, so b becomes discrete. And so if we're extremely q deformed, so for q between 0 and some q critical, everything is finite. Because the minimum value of b, the kind of quantized unit of b, is simply is bigger than b Hagedorn, and I never reach the Hagedorn temperature, and everything is fine. And in the matrix model, this corresponds to a situation where the cut, there's some finite cut now, because it's not double scaled, is perturbatively stable. Now in one matrix models, perturbative stability is trivial because the second derivative of the effective action comes from the eigenvalue repulsion, it's convex. So it's always stable because it's just a repulsion. But in a 2-matrix model, it's not obvious. Yeah, I'll just word it to the wrap up. So in a 2-matrix model, it's not obvious because I generate corrections to the eigenvalue force for the energies from the integrating out O. And when Q is less than Q critical, it remains perturbatively stable. As I take Q to Q critical, the discrete grade here exactly hits the Hagedorn temperature, and there's a divergence in the answer. And in the matrix model, this divergence is a collective zero mode of the eigenvalue distribution. And then I can go past Q critical, but now the eigenvalue solution is perturbatively unstable, so it's a local maximum in some direction, but I can just say I take it anyway. And then I keep going, and I hit an infinite series of poles as I go up to Q critical, as the mesh kind of keeps clicking past the Hagedorn temperature. So that's the structure of this model on the matrix model side. And I think this story is a hint for how non-disordered theories actually work. Of course, here the Q-deformed theory is still a disordered theory because we wrote an integral. Okay? That was built in. But what is the factorization problem, which I'll talk about in the next lecture, is the fact that this looks like the square of a partition function. We get a connected contribution. If we put matter here, it seems to make the connected contribution bigger. It's worse. But if we have a Hagedorn spectrum, then we hit a collective zero mode. That sounds like what happens when you have a winding string. And indeed, the divergence at the Hagedorn temperature is associated with the winding string becoming massless and then past the tachyonic. That's the inverse direction. So somehow the winding modes are collective modes of this eigenvalue distribution of some particular type. But in the Q-deform theory, we're still expanding by definition, we're expanding around the unstable saddle by the definition of the theory. And so we still have disorder. We didn't find the true minimum. And I'm not sure what the true minimum is. You need to know the whole potential. This is probably not the correct physical theory. But I think it's a very strong hint that all of these issues like Euclidean factorization problem require Hagedorn spectrum in the bulk to fix it, and that this is kind of a cartoon of the mechanism.
This is where you begin to see the string theory of the bulk of the.
Exactly, yeah. Yeah. So I'll talk a little bit more about this in the next lecture. So let me stop now.